What if I told you the universe has a secret one so strange, so counter to everything we think we know about reality, that even Einstein himself struggled to accept it? Picture two galaxies separated by billions of light years, so distant that light from one would take longer than the age of our solar system to reach the other. And yet somehow they're connected, not by gravity, not by any force we can see or measure, but by an invisible thread that defies the speed of light itself. This isn't science fiction, it's quantum entanglement, playing out on the grandest stage imaginable, the cosmos. Einstein famously called it spooky action at a distance, a phrase that captures just how unsettling this phenomenon truly is. How can two objects, no matter how far apart, instantly influence each other's behavior without any signal passing between them? It's as if the universe has a hidden rulebook, one that operates outside the limits of space and time. And when we scale this up from tiny particles to entire galaxies, the implications become even more staggering. Could the fabric of reality itself be woven with these invisible connections? Are we looking at a cosmic web far stranger than anything we've ever imagined? That's the mystery we're diving into today. We'll explore how quantum entanglement, a phenomenon once confined to the realm of subatomic particles, might be stretching across the vast emptiness of space, linking galaxies in ways that challenge the very foundations of physics. From the bizarre behavior of entangled particles in labs to the mind-bending possibility that entire regions of the universe are whispering to each other faster than light, this journey will take us to the edge of what science can explain. By the end, you might just find yourself questioning not just the nature of space and time, but what it even means to be separate in a universe that seems determined to prove everything is connected. So buckle up, we're about to peel back the curtain on one of the greatest enigmas in modern physics. To understand how something as vast as a galaxy could be entangled, we first need to grasp the bizarre rules that govern the quantum world. Picture two electrons spinning in perfect harmony, their fates intertwined no matter how far apart they drift. This is entanglement in its simplest form. A connection so profound that measuring the spin of one particle instantly determines the spin of its partner, even if they're on opposite sides of the universe. No signal passes between them, no force mediates the interaction. It's as if space and time simply don't apply. Scientists first observed this in labs with particles like photons or electrons, where entanglement has been tested over distances of hundreds of miles. The results are always the same. The particles act as a single system, defying the classical idea that nothing can travel faster than light. Einstein hated this. He believed reality should be local, meaning objects should only be influenced by their immediate surroundings. But quantum mechanics laughed at that notion. The universe, it seems, doesn't play by the rules we thought were written in stone. Now, take that unsettling idea and scale it up, way up. Instead of tiny particles, imagine two galaxies, each containing hundreds of billions of stars, separated by unfathomable distances. If entanglement can bridge the gap between particles, could it also weave a hidden connection between these colossal structures? Some physicists think so. They speculate that in the early universe, when everything was compressed into a hot, dense soup of particles, entanglement might have been woven into the very fabric of reality. As the cosmos expanded, those quantum links stretched, potentially leaving behind a network of invisible threads tying distant galaxies together. This isn't just wild speculation. There are mathematical models suggesting that entanglement could influence the large-scale structure of the universe, maybe even explaining why galaxies cluster in certain patterns. If true, it would mean the cosmos isn't just a collection of isolated islands, but a vast, interconnected quantum tapestry. The implications are mind-blowing. It challenges our understanding of causality, of separation, of what it even means for two things to be far apart. And if entanglement really does span cosmic distances, we might need to rewrite the textbooks on how the universe works, starting with the very definition of reality itself. Einstein's discomfort with quantum entanglement wasn't just scientific skepticism, it was a fundamental clash of worldviews. The man who reshaped our understanding of space and time couldn't accept that particles might communicate faster than light, dismissing it as spooky action at a distance. Together with physicists Boris Podolsky and Nathan Rosen, he crafted what became known as the EPR Paradox in 1935, a brilliant thought experiment designed to expose what they saw as quantum mechanics' fatal flaw. Their argument was simple yet profound. If measuring one particle instantly determines the state of its entangled partner, regardless of distance, then either information travels infinitely fast, violating relativity, or the particles somehow know their outcomes in advance, suggesting hidden variables. Either way, they concluded, quantum theory must be incomplete. For decades, this remained a philosophical debate until technology caught up with theory. In the 1960s, physicist John Bell devised a mathematical test that could settle the argument experimentally. His groundbreaking work showed that if hidden variables existed, entanglement would obey certain statistical limits. But when scientists finally performed these tests in the 1980s, the results shook physics to its core. Particles violated Bell's limits spectacularly, proving their connection wasn't predetermined but truly instantaneous. Einstein's worst fear had come true. Reality itself seemed to operate with what looked like telepathy at the quantum level. Now imagine extrapolating that unsettling truth to galactic scales. If entangled particles ignore distance, could entire star systems share this bizarre linkage? Some cosmologists speculate that during the Big Bang, when all matter occupied a single point, quantum connections may have formed that never fully severed as the universe expanded. This would mean that galaxies separated by billions of light years might still share spooky quantum threads from their shared origin. The implications rewrite cosmic rulebooks. Perhaps what we perceive as empty space between galaxies isn't empty at all, but threaded with invisible quantum correlations that subtly influence how matter clusters across the universe. This cosmic entanglement might even solve astronomical mysteries. Scientists have noticed that distant quasars' extremely bright galactic cores sometimes exhibit synchronized behavior that defies conventional explanations. Could quantum links established in the early universe be responsible? While mainstream physics still treats this idea cautiously, it's become clear that Einstein's spooky action isn't just a quantum quirk. It might be the hidden scaffolding holding the cosmos together. The irony is profound. The phenomenon he resisted could ultimately explain the large-scale structure of the universe he helped us understand. Making the leap from subatomic particles to entire galaxies isn't just about scaling up the numbers, it's about confronting a fundamental shift in how we perceive reality. At the quantum level, entanglement seems almost manageable, confined to pristine laboratory conditions where we can isolate pairs of photons or electrons. But when we consider galaxies with their chaotic swirls of stars, gas, dust, and who knows what else, the idea feels absurd at first glance. How could something so delicate survive the messy, violent environment of cosmic evolution? Yet the more we examine the possibilities, the harder it becomes to dismiss outright. One compelling angle comes from gravity itself, the architect of cosmic structure. When two galaxies form from the same primordial cloud of matter, their gravitational dance creates an intimate connection that persists across billions of years. Could this gravitational embrace preserve or even generate quantum entanglement? Some models suggest that under extreme conditions, like those near supermassive black holes at galactic centers, space-time itself might act as a kind of quantum messenger, sustaining correlations that would otherwise fade. It's as if the universe has built-in loopholes, allowing entanglement to persist by hitching a ride on gravity's coattails. Then there's dark matter, the invisible scaffolding that holds galaxies together. We still don't know what it is, but its sheer abundance means it could be playing tricks we haven't even imagined. If dark matter particles interact through some quantum channel we haven't discovered yet, they might form a hidden network of entanglement weaving through and between galaxies. Picture this: while the stars and gas we see behave classically, the dark matter halos surrounding them could be engaged in a constant, silent quantum conversation, subtly guiding how galaxies move and cluster over cosmic time. Even more radical is the idea that extra dimensions predicted by string theory but yet to be proven might provide shortcuts for quantum connections. In our three-dimensional view of space, two galaxies appear hopelessly distant. But if higher dimensions exist, their quantum states might be neighbors in ways we can't perceive directly. This wouldn't just explain entanglement at galactic scales. It could redefine what distance even means in the grand scheme of the universe. The most tantalizing clue comes from observations of galaxy pairs that seem to mirror each other in unexpected ways: similar star formation rates, aligned rotation axes, or synchronized activity in their cores. While conventional astronomy explains some of this through past interactions or shared environments, certain patterns resist easy answers. Could these be faint echoes of quantum bonds formed in the universe's infancy? It's a provocative thought, and one that pushes us to reconsider where the boundary lies between the quantum weirdness of the very small and the emergent order of the very large. What we're glimpsing might not just be a scaled-up version of lab experiments, but an entirely new layer of cosmic architecture waiting to be decoded. If there's one thing that makes the universe feel even stranger than quantum entanglement, it's the realization that most of the cosmos is made of stuff we can't even see. Dark matter and dark energy, two of the greatest mysteries in modern physics, account for roughly 95% of everything in existence, and yet we've never directly detected them. They don't emit light, reflect it, or interact with ordinary matter in any way we can easily measure. But what if their invisibility isn't just a limitation of our instruments? What if dark matter and dark energy are hiding something far more profound? A quantum connection stitching the universe together. Think of dark matter as the universe's silent architect. Without it, galaxies would fly apart, their stars scattering into the void. Its gravitational pull is the glue holding cosmic structures together, forming vast, invisible halos around every galaxy. But here's where things get interesting. If dark matter particles are entangled, those halos might be doing more than just providing gravitational scaffolding. They could be acting as a quantum network, a hidden communication channel linking galaxies across unimaginable distances. Picture this: while stars and gas clouds move under the familiar rules of gravity, the dark matter between them might be whispering in a language we're only beginning to decipher, a language where information doesn't need to travel because it's already shared. Dark energy, on the other hand, is the universe's mysterious expansion force. It's causing galaxies to accelerate away from each other, stretching the fabric of space itself. At first glance, this seems like the opposite of entanglement. How can things stay connected while being flung apart? But some theorists speculate that dark energy's relentless push might actually preserve quantum links, like taffy being pulled thin without breaking. The expansion could be stretching space-time, but the quantum correlations woven into it might remain intact, threading through the growing distances like an unbreakable cosmic filament. There's even a wilder possibility. Dark energy itself could be a manifestation of entanglement on a cosmic scale. Just as entangled particles seem to defy local reality, dark energy's uniform influence across the universe, acting equally everywhere at once, might hint at a deeper, non-local connection. It's as if the vacuum of space itself is alive with quantum activity, and what we call dark energy is just the ripple effect of countless entangled particles humming beneath the surface. Of course, these ideas are still speculative, hovering at the edge of established physics. But consider this: when astronomers map the distribution of galaxies across the universe, they find them arranged in a vast, web-like structure, filaments of matter stretching between dense nodes with enormous voids in between. It's eerily similar to how entangled particles might organize if scaled up to cosmic proportions. Could the large-scale structure of the universe be the fingerprint of quantum entanglement, written in the language of dark matter and dark energy? The answer might rewrite not just our understanding of the cosmos, but the very nature of reality itself. To uncover whether the universe's quantum connections stretch across cosmic distances, scientists are turning to one of the oldest snapshots in existence, the cosmic microwave background. This faint glow, often called the afterglow of the Big Bang, is more than just a relic of the universe's fiery birth. It could be a quantum fossil, preserving patterns from a time when everything was so tightly packed that entanglement might have been woven into the fabric of reality itself. Imagine this radiation as a cosmic fingerprint, its subtle variations encoding secrets from when the universe was less than a second old. The cosmic microwave background isn't perfectly uniform. It's speckled with tiny temperature fluctuations, hot and cold spots no larger than a few millionths of a degree. At first glance, these variations seem random, but their arrangement tells a deeper story. Some theorists propose that these patterns could be the amplified echoes of quantum entanglement from the universe's earliest moments. Picture the infant cosmos as a seething quantum soup, where particles were so close together that their fates became inseparable. As the universe expanded, these quantum links might have stretched, imprinting their signatures onto the fabric of spacetime itself, leaving behind subtle correlations in the cosmic microwave background that we can still detect today. This idea gained traction when researchers noticed something peculiar about the way these temperature fluctuations are distributed. Certain pairs of hot and cold spots appear statistically linked in ways that classical physics struggles to explain. It's as if some hidden hand guided their arrangement, creating patterns that resemble the kind of correlations we see in entangled particles. Could this be evidence that quantum connections, once confined to microscopic scales, somehow influenced the large-scale structure of the universe? The possibility is tantalizing, suggesting that the cosmic microwave background isn't just a passive relic but an active messenger from the quantum past. Testing this hypothesis isn't easy. Scientists must sift through mountains of data, looking for statistical anomalies that deviate from standard cosmological models. Some teams have reported hints of these anomalies, subtle excess correlations between distant points in the sky that shouldn't exist if the universe behaved classically. Others remain skeptical, arguing that these signals could be artifacts of measurement errors or incomplete models. But if the evidence holds, it would mean that the cosmic microwave background isn't just a fossil, it's a living record of quantum entanglement written across the entire observable universe. The implications would be staggering. It would suggest that the quantum weirdness we observe in labs today isn't just a small-scale curiosity but a fundamental feature of reality, one that shaped the cosmos from its very first moments. The cosmic microwave background could be the Rosetta Stone that finally deciphers how quantum mechanics scales up to govern the universe at large. And if that's true, then the spooky connections Einstein once dismissed might be the very threads that bind the cosmos together. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate laboratories for testing the limits of quantum entanglement. Picture this, a pair of entangled particles, their fates forever linked, drifting near a black hole's event horizon. One particle falls in, vanishing from our observable universe, while its partner escapes into the void. According to quantum mechanics, their connection should remain unbroken, but here's where things get messy. The black hole's crushing gravity stretches space-time so severely that it could shred the delicate quantum threads binding these particles, forcing us to confront a paradox that threatens the very foundations of physics. This dilemma lies at the heart of the Firewall Paradox, a thought experiment that pits quantum mechanics against Einstein's theory of general relativity. If entanglement persists across the event horizon, information about the swallowed particle should somehow leak back out, violating relativity's rule that nothing escapes a black hole. But if the connection breaks, it would unleash a firewall of intense radiation at the horizon, incinerating anything that falls in. Neither outcome makes sense, which means our understanding of reality might be missing a crucial piece. Enter the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information about particles swallowed by a black hole isn't lost. It's encoded in a quantum hologram on the event horizon's surface, like a cosmic thumb drive storing data in 2 dimensions. Entanglement could be the glue holding this hologram together, with each escaping particle carrying fragments of information about its trapped twin. In this scenario, black holes don't destroy information, they transform it, using quantum connections to preserve what seems lost. The implications ripple far beyond black holes. If entanglement can survive these extreme conditions, it might reveal how quantum mechanics and gravity, the 2 great pillars of physics, finally reconcile. Some theorists even speculate that spacetime itself emerges from a deeper quantum network of entangled particles, like a 3D projection of a 2D code. Black holes, then, aren't just testing entanglement, they're showing us how the universe might fundamentally operate, with every particle, every star, every galaxy woven into a quantum tapestry far stranger than we ever imagined. What makes this especially thrilling is that we're not just theorizing anymore. With breakthroughs like gravitational wave detectors and quantum computers, scientists are edging closer to experiments that could simulate black hole conditions in labs. We might soon witness quantum entanglement pushed to its breaking point, revealing whether these spooky connections truly can span the most violent environments in existence. The answers could rewrite physics and force us to accept that reality, at its core, is far more interconnected than we ever dared dream. Wormholes have long been the stuff of science fiction tunnels through space-time that could let us traverse the universe in a heartbeat. But what if they're not just fantastical plot devices? What if they're real, hiding in plain sight as the very mechanism behind quantum entanglement? This audacious idea, known as the equals EPR Conjecture, suggests that every pair of entangled particles might be linked by a microscopic wormhole, a bridge so tiny it defies detection, yet powerful enough to instantly connect 2 points in space. The theory's name comes from merging 2 groundbreaking concepts, Einstein and Rosen's wormholes and Einstein-Podolsky and Rosen's entanglement paradox EPR. At first glance, they seem unrelated. One deals with spacetime tunnels, the other with quantum weirdness. But dig deeper, and a stunning possibility emerges. Entanglement and wormholes might be 2 sides of the same cosmic coin. Picture an entangled pair of electrons as the mouths of a wormhole, their connection not some abstract quantum handshake but a physical thread woven into the fabric of space-time itself. Now stretch this idea to galactic scales. If microscopic wormholes can link particles, could colossal versions stitch together entire galaxies? The math suggests it's not impossible. In the early universe, when everything was compressed into a singularity, quantum fluctuations might have birthed a network of primordial wormholes. As the cosmos expanded, these tunnels could have stretched alongside it, their endpoints anchoring to regions that eventually grew into galaxies. The result, a hidden subway system beneath the universe, where entangled galaxies aren't just correlated, they're literally connected by space-time shortcuts. This wouldn't just explain entanglement's spooky action. It could solve one of cosmology's biggest puzzles: how information escapes black holes. If a wormhole links particles inside and outside a black hole's event horizon, it might preserve quantum information without breaking physics rules. Scale that up, and galaxies hosting supermassive black holes could be whispering to each other through these cosmic backdoors, their gravitational behemoths acting as natural stabilizers for wormholes that would otherwise collapse. Of course, the leap from particles to galaxies is enormous. Wormholes, even microscopic ones, require exotic matter with negative energy to stay open, something we've never observed. Yet quantum fields can produce negative energy fluctuations, and some models suggest the universe's expansion might stabilize larger wormholes naturally. If true, we could be floating in a web of invisible tunnels, their existence hinted at every time we measure an entangled particle pair. The universe's greatest magic trick might not be action at a distance, but a hidden labyrinth we're only beginning to map. The multiverse theory stretches our imagination to its limits, not just one universe, but an infinite sea of realities, each with its own version of history, physics, and maybe even versions of you. Now take that mind-bending concept and sprinkle in quantum entanglement. If particles can be mysteriously linked across vast distances within our universe, could entangled connections stretch further, threading through the fabric of the multiverse itself? It sounds like science fiction, but some physicists are seriously considering whether entangled galaxies might have counterparts in parallel realities, their quantum states eerily synchronized despite existing in entirely separate universes. Imagine two galaxies, each in a different universe, born from the same quantum fluctuation during the birth of the multiverse. Just as entangled particles in a lab share a hidden bond, these cosmic twins might remain linked, their fates intertwined across the boundaries of reality. Every star that forms in one could have a mirrored counterpart in the other, their evolution playing out in perfect, if invisible, harmony. The idea challenges not just our understanding of entanglement, but the very definition of what a universe even is. Are these parallel realities truly separate, or are they facets of something far larger, a single quantum system writ across existence? The math behind this isn't entirely fantastical. Certain interpretations of quantum mechanics, like the many worlds theory, already suggest that every quantum decision spawns new branches of reality. If that's true, entanglement could be the glue holding these branches together, creating correlations that transcend individual universes. Think of it like a tree with infinite branches. While each twig grows in its own direction, they all share a common trunk, a quantum foundation that connects them in ways we're only beginning to fathom. Critics argue this pushes speculation beyond the bounds of testability, but there are intriguing clues. Some models of string theory predict higher dimensional membranes of reality that could harbor parallel universes hovering just beyond our perception. If these brains occasionally interact, they might exchange quantum information, creating entanglement like links between worlds. Even wilder is the notion that dark energy, the force accelerating our universe's expansion, could be the gravitational pull of neighboring universes subtly tugging at ours through hidden quantum channels. The implications are staggering. If entanglement bridges the multiverse, it would mean that the spooky connections Einstein resisted aren't just a quirk of our cosmos. They're the foundational language of reality itself, written across countless universes. It's a humbling thought. The galaxies we see might be whispering not just to each other, but to versions of themselves in realities we'll never see. And if that's true, then the universe, or rather the multiverse, is far stranger, far more interconnected than we ever dared dream. Detecting quantum entanglement between galaxies isn't just difficult, it's like trying to hear a whisper across a hurricane. Our current telescopes, as powerful as they are, simply weren't designed to catch these subtle quantum signatures. Imagine standing on a beach, trying to spot individual grains of sand moving in sync across miles of shoreline while waves crash all around you. That's the scale of the challenge physicists face when hunting for cosmic-scale entanglement. But the hunt isn't hopeless. Next-generation instruments are on the horizon, tools that might finally crack this cosmic code. Quantum telescopes, still in their infancy, promise to detect light in ways that classical instruments can't, capturing not just brightness and color, but the quantum states of photons arriving from opposite ends of the universe. If two galaxies are entangled, the light they emit might carry telltale correlations in these quantum properties, patterns that would vanish if examined separately, but reveal themselves when compared across vast distances. Gravitational wave detectors could play an equally crucial role. Just as LIGO revealed collisions of black holes by sensing ripples in spacetime, future arrays might pick up subtler vibrations, harmonic patterns in the fabric of reality that could only arise if distant masses are quantum linked. Picture two entangled galaxies moving in ways that defy classical physics, their gravitational waves humming in perfect, inexplicable harmony despite being separated by billions of light years. The real breakthrough might come from combining these approaches. By cross-referencing quantum optical data with gravitational wave signals, scientists could triangulate evidence too faint for any single method to catch. It's like solving a cosmic jigsaw puzzle where half the pieces are hidden in the quantum realm and the other half written in spacetime itself. Of course, skeptics argue this is all speculative, that entanglement's delicate nature would be drowned out by cosmic noise long before we could detect it. But consider this, we once thought measuring quantum effects in single atoms was impossible too. Now we do it routinely. The universe has a habit of revealing its secrets to those patient enough to listen with ever finer instruments. Whether through photons, gravitational waves, or some yet undiscovered quantum fingerprint, the first direct evidence of cosmic entanglement could rewrite not just astronomy textbooks, but our very understanding of reality's interconnected fabric. The Hubble tension is one of modern cosmology's most stubborn puzzles, a glaring mismatch in how fast the universe is expanding, depending on where you look. Measure the rate using nearby galaxies and supernova, and you get one number. Peer back to the cosmic microwave background, the afterglow of the Big Bang, and you get another. The difference isn't huge, but it's persistent, defying every conventional explanation. Could this discrepancy be more than just a measurement error? Could it be a whisper from the quantum realm, a hint that entanglement is subtly shaping the cosmos on the grandest scales? Here's where things get provocative. If entangled galaxies share an instantaneous connection, one that bypasses the speed of light, their synchronized behavior might skew our measurements in unexpected ways. Picture two galaxies quantum linked since the dawn of time. When we observe one, its properties might already reflect the state of its entangled partner, even if they're billions of light years apart. This could create subtle biases in how we calculate distances and redshifts, the very tools we use to gauge cosmic expansion. The result, a universe that appears to expand at slightly different rates depending on which thread of the quantum web we're tugging on. The idea gains traction when you consider how we measure the Hubble constant. Local methods rely on observing stars and galaxies, assuming their light travels to us unimpeded by any hidden quantum handshakes. But if entanglement subtly alters how light redshifts or how supernovae brighten and fade across vast distances, our calculations could be missing a critical variable. Meanwhile, the cosmic microwave background reflects the universe's state before galaxies formed, before entanglement could weave its web. The tension between these two methods might not be an error at all, but evidence of quantum connections operating behind the scenes. Critics argue this is a stretch, that entanglement's delicate effects would be swamped by cosmic noise long before influencing something as coarse as expansion rates. But remember, quantum mechanics once seemed too fragile to explain anything beyond tiny particles, yet here we are, pondering its role in galactic evolution. The universe has a way of scaling up the seemingly insignificant. If quantum entanglement really does thread through the cosmos, its fingerprints might be hiding in plain sight, woven into the very data that's baffling astronomers today. What makes this hypothesis so tantalizing is that it's testable, at least in principle. Future telescopes could hunt for anomalous correlations between distant galaxies' patterns that defy classical causality. If pairs of galaxies exhibit synchronized properties that can't be explained by shared history or local interactions, quantum entanglement might be the only explanation left standing. The Hubble tension, then, wouldn't just be a problem to solve, it could be the first observable tremor of a quantum universe, shaking the foundations of how we measure reality itself. Perhaps Einstein's spooky action wasn't just a quirk of tiny particles. Perhaps it's the hidden architecture of spacetime, quietly guiding the universe's expansion in ways we're only beginning to fathom. The Hubble tension might be more than a discrepancy. It could be our first glimpse into a cosmos far stranger, far more interconnected than we ever imagined. If quantum entanglement is so powerful that it can bind galaxies across the cosmos, why doesn't the entire universe shimmer with these spooky connections? The answer lies in a phenomenon called decoherence, the relentless interference that usually tears quantum states apart. Picture a perfectly still pond where two entangled particles create ripples moving in perfect sync. Now toss a handful of pebbles into that pond. The once clear patterns dissolve into chaos as waves collide and cancel each other out. That's decoherence in action, the constant bombardment from the environment that destroys fragile quantum links, forcing particles to pick a state and behave classically. This is why we don't see quantum weirdness in everyday life. A coffee cup doesn't exist in multiple places at once because its trillions of atoms are constantly jostled by air molecules, light, and even the faintest cosmic rays. But here's the puzzle. If decoherence is so efficient at wiping out quantum effects, how could something as vast and chaotic as a galaxy possibly stay entangled? The sheer scale of galactic environments, supernova explosions, swirling magnetic fields, and torrents of radiation should shred any delicate quantum connection in an instant. And yet, the tantalizing possibility remains that some galaxies might still be whispering to each other across the void. One radical explanation is that entanglement isn't as fragile as we think. In the bizarre world of quantum field theory, certain states can become topologically protected, like knots in spacetime that can't be untangled no matter how hard the universe tries. These robust quantum links might form in the extreme conditions of the early cosmos, where temperatures and densities were so high that particles could forge connections too deep for decoherence to sever. As the universe expanded, these bonds stretched but never broke, woven into the fabric of reality itself. Another possibility, gravity might be the guardian of cosmic entanglement. While we usually think of gravity as the weakest of nature's forces, its cumulative effect over galactic scales could create a kind of quantum sanctuary. Just as a black hole's immense gravity warps spacetime into a protective horizon, the collective gravitational field of a galaxy might shield entangled states from environmental disruption. It's as if the galaxy itself acts like a giant Faraday cage, insulating its quantum connections from the chaos outside. The wildest idea of all is that we're missing a fundamental piece of physics, one that blends quantum mechanics with gravity in ways we haven't yet imagined. Some theories suggest that spacetime itself emerges from a deeper layer of entangled quantum information. If that's true, then the entanglement we're trying to detect isn't happening inside the universe. It is the universe, with galaxies merely the visible knots in a quantum tapestry we're only beginning to unravel. This isn't just theoretical hand-waving. Scientists are already looking for fingerprints of cosmic-scale entanglement in the subtle patterns of galaxy distributions and the cosmic microwave background. If they find them, it would mean decoherence isn't the end of the story, just a local effect in a far stranger, far more connected cosmos. The universe might not be playing by the rules we wrote. It could be following a quantum playbook we've only glimpsed in the margins. Time might be the most stubborn illusion in the universe, a one-way street we all assume can't be reversed. But quantum entanglement doesn't just defy space. It laughs at our classical notions of cause and effect. Imagine two galaxies, their fates intertwined since the dawn of time, not just communicating faster than light, but potentially sending signals backward through time itself. This isn't science fiction, it's a legitimate interpretation of quantum mechanics that could rewrite our understanding of cosmic history. The idea hinges on something called retrocausality, where an effect precedes its cause. In lab experiments, entangled particles seem to decide their states only when measured, as if the act of observation reaches backward in time to influence their past behavior. Scale this up to galaxies, and the implications become staggering. Picture a pair of entangled galaxies where a supernova explosion in one somehow influences the star formation rate of its partner, not just instantly across space, but before the explosion even occurs from our perspective. It's as if the universe keeps editing its own script, with quantum connections threading through time as effortlessly as they ignore distance. Critics argue this violates relativity's strict no-time travel rule, but quantum mechanics has never played by classical rules. Some interpretations suggest that retrocausality doesn't create paradoxes because the timeline self-corrects like a cosmic game of Tetris, where every move reshapes the past just enough to keep the physics consistent. If true, entangled galaxies might be engaged in a delicate dance where their pasts and futures are constantly renegotiated. With changes so subtle, we'd need impossibly precise instruments to detect them. The wildest part, we might already have evidence hiding in plain sight. Certain anomalies in galaxy distributions, unexpected symmetries or clusters that defy standard models, could be scars from quantum adjustments made to the universe's early conditions. It's as if the cosmos is a painting where the artist keeps dabbing at the canvas, tweaking details long after the first strokes dried. While mainstream physics remains cautious, the possibility forces us to confront a profound question. Is time truly fundamental, or just an emergent property of deeper quantum connections? If entangled galaxies can whisper across billions of years in both directions, then the arrow of time might not be an absolute law, just a local habit of our corner of reality. The universe, it seems, keeps its options open. The holographic principle turns our perception of reality inside out. What if the three-dimensional universe we see is just a shadow, a projection from a two-dimensional surface where all the true information is stored? Imagine the cosmos as a movie screen with galaxies merely pixels flickering in a grand illusion. But here's the twist: those pixels aren't isolated dots. They're entangled, they're quantum connections weaving the very fabric of what we perceive as space, time, and even gravity. This radical idea emerged from studying black holes, where physicists realized the information swallowed by these cosmic voids couldn't just vanish. Instead, it seemed to be encoded on their event horizons, the ultimate 2D surfaces. Scale that up, and the entire universe might operate the same way, with every star, every planet, and every galaxy acting as holographic projections from a hidden quantum layer. The kicker: entanglement could be the glue holding this illusion together. Just as a 3D image emerges from the precise alignment of pixels on a 2D screen, the depth and structure of our universe might arise from quantum links stitching together information stored on its boundaries. Think of two entangled galaxies not as separate objects, but as reflections of a single piece of data written on the cosmic horizon. Their connection isn't just spooky, it's foundational, like 2 points on a hologram that only make sense when viewed together. This would mean the vast distances between them are an illusion, a byproduct of how the hologram renders depth. In reality, they're neighbors in the encoded data, their apparent separation no more real than the distance between pixels on your phone screen. The implications rewrite physics. Gravity, long described by Einstein as the curvature of spacetime, might instead be a side effect of entanglement, a kind of quantum tension in the hologram's weave. Dark energy, perhaps just the universe recalibrating its information density as it expands. Even time could lose its status as a fundamental force, becoming a derived property of how the hologram updates itself. Skeptics argue this sounds more like philosophy than science, but the math holds surprising weight. Certain quantum theories predict precise correspondences between events in 3D space and calculations on a 2D boundary, like a cosmic cheat sheet where the answers match perfectly. And if entangled galaxies are indeed pixels in this hologram, we might find clues in the way their light carries quantum information, subtle correlations that defy classical explanations. The most mind-bending possibility: if the holographic principle is true, then searching for cosmic entanglement isn't just about finding hidden connections, it's about decoding reality's source code. The universe isn't merely entangled, it might be entanglement, a vast quantum network painting the illusion of depth, one spooky pixel at a time. Quantum gravity has been the Everest of theoretical physics, a peak so daunting that even the brightest minds struggle to find a path upward. For over a century, we've lived with a glaring schism. Quantum mechanics rules the tiny world of particles with eerie precision, while Einstein's general relativity governs the cosmic dance of stars and galaxies. But where these two titans meet, at the center of black holes, at the instant of the Big Bang, our equations explode into nonsense. Something fundamental is missing. And increasingly, physicists suspect that something might be quantum entanglement, the very phenomenon that once made Einstein shudder. Picture spacetime not as a smooth, continuous fabric, but as a shimmering network of interconnected nodes, each linked by threads of entanglement. This is the heart of loop quantum gravity, a radical framework where space itself is woven from discrete, quantized loops. In this view, the fabric of reality isn't just stitched together by gravity, It's knitted by quantum connections, with every twist and knot giving rise to what we perceive as distance, curvature, even time. When two entangled particles instantly influence each other across vast distances, they're not bending the rules of space-time. They're revealing its true, quantum-knitted nature. String theory offers an equally mind-bending perspective. Imagine the universe's fundamental building blocks not as points, but as vibrating strings, with each note they play corresponding to a different particle. But here's the twist. These strings might be entangled across hidden dimensions, their vibrations harmonizing in ways that generate gravity itself. In some versions of the theory, entangled strings could create microscopic wormholes, Einstein-Rosen bridges, linking distant points in space. Scale this up, and the gravitational pull between galaxies might just be the macroscopic echo of countless quantum threads humming beneath the surface. The most tantalizing clue comes from black holes. When matter falls into one, classical physics says it's lost forever. But quantum mechanics insists information can't vanish, it has to go somewhere. The resolution, entanglement. Theorists like Juan Maldacena and Leonard Susskind propose that particles inside and outside a black hole remain quantum-linked, with their connection forming a bridge through which information secretly escapes. If true, this AR equals EPR conjecture suggests that entanglement doesn't just mimic gravity. It might be gravity, with every gravitational attraction we observe traceable to an underlying quantum handshake. Of course, skeptics point out the elephant in the room. We've never directly observed quantum gravity's effects, but new experiments are inching closer. Some labs are cooling massive objects to near absolute zero, hunting for quantum behavior in ever larger systems. Others are probing spacetime's granularity using ultra-precise lasers, or watching for entangled particles near black hole analogs in metamaterials. Even gravitational wave detectors like LIGO might someday catch hints of quantum froth in the ripples from colliding neutron stars. The stakes couldn't be higher. If entanglement really is the missing stitch between quantum mechanics and gravity, it wouldn't just solve equations, it would redefine reality. Time, space, even causality might emerge from a deeper layer of quantum connections, like a 3D hologram projected from a 2D code. The universe wouldn't just contain entangled particles. It might be an entanglement, a vast cosmic web where every galaxy, every star, every atom is whispering to the others in a language we're only beginning to decipher. Simulating the quantum entanglement of galaxies isn't like running a typical physics experiment. It's more like trying to recreate the entire internet inside a single computer chip. Even our most powerful supercomputers, capable of performing quintillions of calculations per second, buckle under the weight of modeling such an impossibly complex system. Think about it. A single galaxy contains hundreds of billions of stars, each with planets, asteroids, and swirling clouds of gas, all potentially interacting through quantum connections we can't directly observe. The sheer scale of variables would make any simulation grind to a halt before it even began. But here's where scientists get clever. Instead of attempting to model every atom, they're focusing on simplified versions of reality, like sketching the outline of a galaxy instead of painting every star. By stripping away layers of complexity, researchers can isolate the core behaviors of entangled systems. Imagine a digital experiment where two simulated galaxies are represented not by countless particles, but by a handful of quantum nodes connected in specific patterns. These nodes act as stand-ins for the key properties that might carry entanglement, dark matter distributions, gravitational wave signatures, or even the polarized light from quasars. The results are already revealing surprises. Some simulations show that entangled galaxies could leave faint statistical fingerprints in how they rotate or cluster together. When one galaxy's star formation rate spikes, its entangled counterpart might exhibit a delayed but matching burst of activity, like cosmic twins separated at birth but still mirroring each other's lives. Other models suggest that entangled pairs could warp spacetime around them in subtly different ways than classical physics predicts, creating telltale distortions in the paths of light traveling between them. Of course, these digital experiments come with caveats. Simplified models inevitably leave out real-world chaos, supernova explosions, black hole mergers, and interstellar collisions that could scramble quantum connections. That's where hybrid approaches come in. Teams are now combining AI with quantum algorithms, training neural networks to spot potential entanglement signatures in existing astronomical data. It's like teaching a detective to recognize the faintest of clues in a case where the crime scene spans billions of light years. The ultimate goal isn't perfection, it's direction. Even rough simulations can point telescopes where to look, hinting at which galactic pairs might defy classical explanations. And as quantum computers mature, their ability to handle entanglement natively could unlock simulations with unprecedented fidelity. We might never perfectly replicate the universe inside a machine, but every simplified model brings us closer to answering the haunting question: is the cosmos humming with quantum connections we've only just begun to imagine? What if the greatest technological leap for an advanced civilization wasn't faster than light travel, but something far stranger, harnessing the quantum threads woven between galaxies? Picture a society so advanced they've moved beyond radio signals and lasers, instead tapping into the universe's own hidden infrastructure, the spooky connections of entangled stars. While this sounds like pure science fiction, the underlying physics doesn't outright forbid it. If entanglement truly links distant corners of the cosmos, why couldn't a sufficiently advanced species exploit it? Consider how humanity's own communication evolved from smoke signals to fiber optics, each leap relying on deeper understanding of nature's laws. An alien civilization millions of years ahead of us might have cracked quantum entanglement's code, using it to build a galactic-scale internet. Here's how it could work. Entangled particle pairs, separated during the universe's infancy, could act as cosmic telegraph wires. Manipulating one particle's state would instantly alter its partner, no matter the distance. No waiting centuries for messages to cross interstellar space, just real-time communication through what amounts to quantum Morse code. The energy savings alone would be staggering, bypassing the need for colossal transmitters to beam signals across light years. But communication might just be the beginning. Some theorists speculate that entanglement could be harvested for energy, not by breaking physics conservation laws, but by exploiting subtle quantum imbalances. Imagine a Dyson sphere not around a star, but around an entangled particle source, extracting work from the correlated states of distant systems. It's a stretch, yes, but no more so than nuclear power would have seemed to medieval alchemists. The real kicker: we might already have clues that such civilizations exist. Astronomers have detected bizarre cosmic anomalies, galaxies with inexplicably synchronized behaviors, or quasars pulsing in rhythms that defy conventional explanation. While natural processes could account for these, they also fit the profile of a universe where someone, or something, has learned to pull entanglement's levers. Of course, skeptics argue that decoherence would render cosmic-scale quantum engineering impossible, that the chaos of interstellar space would scramble any delicate entanglement. But what if advanced beings have found ways to stabilize these connections? Black holes, with their space-time warping gravity, might serve as natural quantum repeaters, reinforcing entanglement across vast distances. Or perhaps they've mastered error-correcting code so sophisticated they can preserve quantum coherence against all odds, like a pianist playing flawlessly in a hurricane. The most tantalizing possibility isn't just that aliens could use entanglement, it's that they might leave detectable signatures in the process. Quantum communication could produce subtle statistical patterns in starlight, or create telltale distortions in the cosmic microwave background. Future telescopes attuned to these quantum fingerprints might one day spot the equivalent of cosmic switchboards humming between galaxies. Whether any of this is possible remains an open question, but the mere idea reshapes how we imagine advanced life. Instead of searching for radio waves or megastructures, we might need to look for the universe's quietest whispers, the faintest ripples in the quantum fabric, hinting that we're not the only ones pondering the spooky connections binding the cosmos. The idea that galaxies might be entangled doesn't just rattle our understanding of physics, it shakes the very foundations of how we perceive reality. If distant corners of the cosmos are bound by invisible quantum threads, what does that say about the nature of existence itself? For centuries, humans have clung to the notion of separateness, that objects, planets, even minds are distinct and isolated. But entanglement whispers a radical alternative. The universe might not be a collection of disconnected parts, but a single, seamless whole. Philosophers have danced around this idea for millennia. Ancient Eastern traditions like Advaita Vedanta spoke of a unified consciousness where individuality is an illusion. Western thinkers from Spinoza to Hegel envisioned reality as an interconnected substance where every piece reflects the whole. Now, quantum physics might be handing us the mathematical framework to test these age-old intuitions. If entangled galaxies behave as one system regardless of distance, it suggests that the universe operates not as a machine with discrete cogs, but as a living tapestry where every thread is woven into the same grand design. This raises a question so profound it borders on the mystical. Could the cosmos possess a form of cosmic consciousness? Before you dismiss this as New Age speculation, consider that some serious scientists are exploring the idea. Integrated information theory, a framework developed by neuroscientist Giulio Tononi, suggests that consciousness arises from the interconnectedness of a system's parts. Apply that to entangled galaxies, and the universe itself might meet the criteria for a conscious entity, not in the human sense, but as a vast, self-aware network where information flows instantaneously across space-time. Even without venturing into consciousness, the implications are staggering. Causality, the bedrock of science, assumes that causes precede effects in an orderly sequence. But entangled systems defy this, acting in unison without any clear first move. If galaxies share this bond, then events we perceive as isolated, a supernova here, a quasar's flare there, might be manifestations of a deeper, non-local unity. Time itself could be an emergent property, a way for the universe to experience its own entanglement in a linear narrative. The resistance to these ideas is understandable. They blur the line between physics and philosophy, between measurement and meaning. Einstein himself recoiled from the notion of a dice-playing God, let alone a universe that might resemble a thinking organism. Yet the math keeps pointing us toward a reality far stranger than our classical intuitions can grasp. Whether we call it quantum interconnectedness, cosmic consciousness, or simply the universe's hidden architecture, one thing is clear: the old paradigm of separateness is crumbling. We're left staring at a cosmos that might not just contain mysteries, but be one vast, whispering mystery itself. Quantum entanglement has long been a playground for storytellers, its eerie implications sparking wild narratives across science fiction. From Star Trek's teleporters to Doctor Who's time-warping weeping angels, pop culture latches onto the idea of instantaneous connections across space, even if the science gets stretched thinner than space-time near a black hole. Take the iconic, spooky action scene in Interstellar, where Cooper communicates across dimensions via a tesseract, a visually stunning metaphor for entanglement, even if it plays fast and loose with the physics. These stories thrive because they tap into something primal, our longing to believe the universe is more interconnected than it appears. But pop culture's love affair with entanglement isn't just about flashy special effects. It mirrors humanity's struggle to grasp the ungraspable. The X-Files episode, Biogenesis, imagined alien DNA carrying quantum-linked messages, a poetic take on how entanglement might encode cosmic secrets. Even Rick and Morty's absurdist humor leans into it, with interdimensional cables and entangled memories highlighting how absurd and hilarious non-locality could get if scaled to everyday life. These tales, however exaggerated, reveal a deeper truth. Entanglement fascinates us because it hints at a universe where separation might be an illusion. Sometimes fiction even nudges science forward. The telepathic Ansible in Ursula K. Le Guin's novels, a device allowing instant communication across light years, directly inspired physicists to explore whether entanglement could revolutionize messaging. While we now know quantum links can't transmit information faster than light, the dream persists in projects like quantum satellites, which use entangled photons to create ultra-secure networks. Art, in this case, didn't predict reality, but it certainly fueled the imagination needed to chase it. Where pop culture often falters is in conflating entanglement with outright magic. Marvel's quantum realm reduces it to a plot device for time travel, while Stranger Things' Upside Down treats it like a supernatural rift. These versions prioritize drama over nuance, but they also serve a purpose. They make the incomprehensible feel tangible. When audiences watch Ant-Man scramble through quantum tunnels or see Fringe's parallel universes bleed together, they're not learning textbook physics. They're glimpsing the emotional weight of a universe that might be far stranger than textbooks allow. The most intriguing portrayals, though, are the ones that flirt with realism. Arrival's heptapod language, rooted in non-linear time, echoes the way entanglement defies causality. Black Mirror's USS Callister explores identity duplication through quantum data copying, a chilling take on how entangled states might blur the line between original and copy. These stories succeed because they respect the science enough to let its weirdness shine, proving that the truth, spooky action and all, can be just as compelling as any fiction. What ties these portrayals together isn't accuracy, but awe. Whether it's a blockbuster bending the rules or an indie film pondering cosmic unity, they all channel the same wonder that grips physicists staring at lab data. Entanglement in pop culture is less about getting it right and more about asking, what if? And in that, they're not so different from the scientists peering into the quantum abyss, daring to imagine a universe where everything whispers to everything else. Let's set the record straight. Cosmic entanglement isn't a sci-fi teleportation device or some mystical force bending reality to its will. It's easy to see why the confusion exists. When particles influence each other instantly across billions of light years, it feels like magic. But here's the crucial distinction: entanglement doesn't move anything, not matter, not energy, not even information in the traditional sense. You couldn't use it to zap a spaceship across the galaxy or send a message faster than light, no matter how advanced your technology. What's actually happening is far subtler, and in some ways even more profound. Take the classic misconception that entangled particles are communicating. They're not. There's no signal racing between them, no hidden radio wave carrying data faster than light. Instead, Think of entanglement like a pair of dice that always land on matching numbers, no matter how far apart you roll them. The correlation is baked in from the moment they're created. It's just that neither die chooses its number until you look. This is why Einstein bristled at the idea. It suggests the universe operates on a kind of prearranged harmony that defies our everyday intuition about cause and effect. Another common mix-up, equating entanglement with wormholes or shortcuts through spacetime. While theories like ER equals EPR propose fascinating links between the two, entanglement itself doesn't create tunnels or warp distance. Those hypothetical wormholes would require exotic matter and conditions we've never observed, whereas entanglement is routinely demonstrated in labs with humble photons and electrons. The key difference is scale. What works for particles might not translate to galaxies without mechanisms we don't yet understand. Then there's the myth that entanglement could power futuristic tech like instant messaging across the cosmos. Here's the catch: while measuring one particle reveals its partner's state, you can't control what that state will be. It's like having a cosmic Morse code where the dots and dashes are random. You'd need a second, slower channel like a radio signal to decode the meaning, defeating the purpose. This isn't just a technical hurdle, it's baked into quantum mechanics itself, a safeguard against paradoxes that would upend relativity. The biggest misunderstanding, though, is treating entanglement as proof that anything is possible in quantum physics. Sure, the rules are weird, but they're still rules. Entanglement doesn't mean galaxies can suddenly swap places or that consciousness collapses reality, despite what some pop culture takes suggest. It's a precise, mathematically grounded phenomenon with boundaries, ones that keep it from becoming a deus ex machina for every unsolved mystery. So why does this matter? Because stripping away the hype reveals entanglement's true marvel. It's not a cosmic cheat code, but a glimpse into a deeper layer of reality where separation might be an illusion. The real magic isn't in breaking the universe's rules, it's in discovering that the rules were far stranger than we ever imagined, and that perhaps is more thrilling than any fiction. The next decade of cosmic exploration might finally lift the veil on quantum entanglement's role in shaping the universe if we know where to look. Instruments like the James Webb Space Telescope aren't just marvels of engineering, they're time machines peering back to an era when the first galaxies were forming. Imagine capturing light from galaxies so ancient their stars were born when quantum entanglement might still have been weaving the cosmos together. Webb's infrared eyes could spot anomalous correlations in these infant galaxies' patterns where paired structures rotate in sync or exhibit matching star formation rates despite being too far apart to influence each other classically. These wouldn't be smoking guns but whispers, hints that quantum threads survived the universe's chaotic adolescence. Meanwhile, the LISA gravitational wave detector, set to launch in the 2030s, will listen for ripples in spacetime with unprecedented sensitivity. While designed to catch collisions of supermassive black holes, LISA might also detect something subtler: harmonic vibrations in the cosmic web that defy conventional explanations. If entangled galaxies subtly tug on spacetime in coordinated ways, their gravitational waves could carry a distinctive fingerprint, like two tuning forks humming the same note across the void. The challenge will be untangling these signals from the cosmic noise, a task that'll require algorithms trained to recognize quantum harmony in a symphony of chaos. Then there's the fledgling field of quantum astronomy, where telescopes don't just collect light but measure its quantum states. Projects like the proposed Quantum Cosmic Microwave Background Imager aim to analyze the polarization of ancient photons for entanglement signatures. If the universe's oldest light still carries traces of quantum linking from the Big Bang, It could show up as statistical anomalies, tiny deviations from randomness that mirror the correlations seen in lab experiments with entangled particles. The wild card, quantum computers themselves. As these machines scale up, they could simulate cosmic entanglement in ways classical computers never could, modeling how quantum links might behave across galactic distances. Imagine programming a quantum computer with the known properties of dark matter and dark energy, then watching how entangled nodes evolve over billions of simulated years. The results might reveal whether entanglement could realistically persist in the real cosmos, or if decoherence would shred it to pieces. But the most thrilling possibility isn't just confirming cosmic entanglement, it's discovering something entirely unexpected. Every time humanity builds a new window on the universe, from Galileo's telescope to Hubble, we've stumbled upon phenomena that rewrite the textbooks. As these next-generation tools come online, they might uncover quantum connections operating in ways no theorist predicted, revealing that the universe's hidden wiring is even stranger than we dared imagine. The answers won't come easily, but one thing's certain: the cosmos has been keeping quantum secrets for 13 billion years. Soon, we might finally be ready to listen. Imagine a future where humanity holds the power to tweak the quantum threads binding galaxies together, like a cosmic engineer rewiring the universe's hidden circuitry. The idea sounds like the plot of a sci-fi epic, but as our understanding of entanglement deepens, so does the unnerving possibility that we might one day manipulate it. And with that power comes a question that should give us pause. If we pull on these invisible strings, could we accidentally unravel the very fabric holding galaxies in place? The ethical dilemmas here are staggering. Take something as seemingly benign as attempting to use entangled particles for faster-than-light communication. The process might require stabilizing or amplifying quantum links across interstellar distances, but what if that stabilization disrupts the delicate balance of entanglement already woven into cosmic structures? Like removing a single thread from a tapestry, meddling with one connection could have cascading effects we can't predict. Galaxies might rely on these quantum links in ways we don't yet understand. Their rotations, star formation rates, or even dark matter distributions subtly guided by entanglement's silent hand. Tampering could risk triggering chain reactions like knocking over the first domino in a line stretching billions of light years. Then there's the issue of unintended consequences. Entanglement doesn't play by classical rules, so our interventions might not either. Suppose we develop technology to entangle two distant stars for energy harvesting or data transfer. In a classical system, you'd expect localized effects, but quantum systems don't respect boundaries. The act of creating new entanglement could overwrite or interfere with existing quantum links, like shouting into a crowded room and accidentally altering 1,000 whispered conversations at once. The result: cosmic-scale side effects, perhaps disrupting gravitational equilibriums or even altering the trajectories of star systems. But the biggest ethical hurdle isn't just physics, it's philosophy. If entanglement truly connects distant regions of space, then manipulating it isn't just engineering. It's editing the universe's foundational code. Who gets to make those decisions? A single government, a corporation, the scientific community. The stakes dwarf any ethical debate we've faced before, from nuclear weapons to genetic engineering. This isn't just about risking our planet or even our solar system. It's about potentially reshaping reality for civilizations we don't even know exist. History offers a sobering parallel: the early days of radio, when humanity began broadcasting into the cosmos without considering who or what might be listening. Now imagine that recklessness applied to quantum engineering. we could be altering cosmic infrastructure that other intelligent beings rely on, like unknowingly cutting a power line that fuels an entire city. The principle of non-interference, long debated in hypotheticals about alien contact, might need to extend to the quantum realm. And let's not forget the existential irony. If entanglement links us to distant galaxies, then any attempt to manipulate it could loop back on us in ways we can't foresee. Like a snake eating its own tail, our experiments might ripple through the quantum web and return to haunt us, rewriting local physics or even tampering with Earth's own place in the cosmic dance. The only ethical path forward is humility and patience. Before we even consider touching the universe's quantum wiring, we'd need a framework akin to the planetary protection protocols guiding space exploration, but scaled to cosmic significance. That means international collaboration, exhaustive simulations, and perhaps even a moratorium on large-scale quantum experiments until we're certain we understand the repercussions. After all, the universe has been entangled for 13 billion years without our help. The burden of proof isn't on nature to justify its design, it's on us to prove we won't break what we don't yet comprehend. Parallel research into quantum biology is uncovering something astonishing. Living systems might already be exploiting entanglement right under our noses. Think about photosynthesis, where plants convert sunlight into energy with near-perfect efficiency. Scientists once assumed this was a classical process, but experiments now suggest quantum coherence, a close cousin of entanglement, plays a crucial role. Inside a leaf, energy doesn't hop randomly between molecules. It explores multiple pathways simultaneously, as if guided by an invisible quantum hand. This isn't just a fluke of nature, it's a finely tuned quantum optimization, honed by billions of years of evolution. If biology can harness quantum effects in warm, messy environments, why couldn't the universe at large? The parallels between biological and cosmic entanglement run deeper than we ever imagined. Take migratory birds, for instance. They navigate using Earth's magnetic field, but the mechanism has long puzzled scientists. Recent studies point to entangled electron pairs in specialized proteins within their eyes, acting like a quantum compass. These fragile quantum states persist despite the noise and heat of living tissue, a feat that defies traditional assumptions about decoherence. Now scale that idea up to galaxies. If biological systems can protect entanglement in chaotic conditions, perhaps cosmic structures do the same, using gravity or dark matter as a stabilizing force instead of proteins. Even human biology might hold clues. Our sense of smell, once thought to rely solely on molecular shape, could involve quantum tunneling, where electrons momentarily teleport across barriers in receptor proteins. It's as if life has been quietly using quantum tricks for eons, while physicists assumed such behavior was confined to ultra-cold labs. This raises a provocative question. If entanglement is robust enough to operate in a bird's eye or a leaf, could it also endure the turbulent nurseries where galaxies are born? The overlap between quantum biology and cosmology isn't just poetic, it's practical. Biological systems offer a testing ground for how entanglement might function in noisy, complex environments, something lab experiments struggle to simulate. For example, the way photosynthetic proteins shield quantum states from disruption might mirror how dark matter halos preserve entanglement between galaxies. By studying nature's solutions, we could uncover universal principles for maintaining quantum coherence across staggering scales. Critics argue that biological quantum effects are too fleeting to compare with cosmic phenomena, but that might be missing the point. Life doesn't need entanglement to last forever, just long enough to be useful. Similarly, galaxies might only require fleeting quantum correlations at critical moments, like during their formation or collisions, to leave lasting imprints on the universe's structure. The key insight here is adaptability. Whether in a cell or a supercluster, nature seems to exploit quantum connections where they offer an advantage, then let them fade when their job is done. This convergence of biology and astrophysics hints at something profound. Entanglement might not be a rare quantum oddity, but a fundamental tool woven into the fabric of reality at every scale. From the spin of an electron in a bird's eye to the dance of galaxies across the void, the same rules could be at work, manifesting differently but rooted in the same quantum bedrock. As researchers peer deeper into both living cells and telescopic images, they're not just studying isolated phenomena, they're piecing together a unified theory of how the universe builds complexity, one entangled connection at a time. One of the greatest challenges in explaining quantum entanglement isn't the science itself, it's untangling the web of pop culture myths that have wrapped themselves around the concept. For every accurate documentary or well-researched article, there are a dozen sci-fi plots and viral headlines twisting entanglement into something it's not. The result, a public that either dismisses it as fantasy or expects it to function like a Star Trek transporter. Scientists face an uphill battle. How do you convey the mind-bending truth without feeding the hype or reducing it to meaningless buzzwords? The heart of the problem lies in translation. Quantum mechanics speaks in probabilities and wave functions, while most of us think in cause and effect. Take the phrase spooky action at a distance. It's vivid and memorable, but it also implies a kind of ghostly communication that doesn't actually happen. A better approach might be to borrow from everyday experiences. Think of entanglement like a perfectly synchronized dance duo separated by an ocean. Even though they can't see each other, every move one makes mirrors the others, not because signals are flying between them, but because their routines were choreographed from the start. The magic isn't in communication, it's in the shared history that makes their coordination inevitable. Visual storytelling could be another powerful tool. Instead of relying on dry equations or flashing particle animations, imagine interactive simulations where viewers tweak variables and see how entanglement behaves in real time. Picture a digital lab where you can entangle virtual photons, then try and fail to send a message faster than light, discovering firsthand why it's impossible. Hands-on experiences like these don't just correct misconceptions, they build intuition for how quantum rules differ from classical ones, but clarity shouldn't come at the cost of depth. Too often, popular science resorts to vague metaphors that leave out the very thing that makes entanglement fascinating: its defiance of classical logic. Instead of saying entangled particles communicate, we could explain the actual math behind Bell's theorem, not as abstract symbols but as a cosmic game of chance where the odds simply don't add up unless particles are fundamentally linked. It's a trickier conversation, sure, but audiences deserve to know why physicists find this so revolutionary, not just that it's weird. The stakes are higher than just public understanding. Misconceptions about entanglement fuel everything from quantum healing scams to misguided policy debates about funding cutting-edge research. When people expect instant interstellar communication or Star Trek tech just around the corner, they grow disillusioned with real science that moves incrementally. On the flip side, those who dismiss entanglement as pseudoscience miss its genuine potential, from unbreakable encryption to ultra-precise sensors. Perhaps the solution isn't dumbing things down, but inviting people in. Citizen science projects like those analyzing quantum data from home computers, or YouTube explainers that tackle the math without flinching, can bridge the gap between mystery and mastery. The goal isn't to make entanglement easy, it's to make it intriguing enough that the complexity feels worth unraveling. After all, the universe doesn't owe us simplicity. But with the right tools, we can learn to speak its quantum language, one clarified concept at a time. Funding the search for cosmic entanglement isn't just writing checks to scientists, it's investing in the future of human knowledge itself. Think about how much we've spent on particle colliders like the Large Hadron Collider or telescopes like James Webb. These aren't just machines, they're time machines, peeling back layers of reality to show us how the universe really works. The hunt for quantum connections between galaxies might sound like abstract physics, but history shows that understanding fundamental truths has a way of sparking revolutions we never see coming. Consider gravity. Newton's apple moment wasn't just about fruit falling. It laid the groundwork for everything from ocean navigation to spaceflight. Quantum mechanics, once dismissed as impractical math, now powers every smartphone and MRI machine. The pattern's clear. When we decode nature's deepest rules, society reaps benefits we couldn't have predicted. Cosmic entanglement could be the next leap. If we confirm that galaxies share quantum links, it wouldn't just rewrite textbooks, it might unlock technologies we can't yet imagine. Imagine energy systems tapping into non-local quantum states, or communication networks secured by the universe's own encryption. But let's address the elephant in the room, the cost. Projects like the proposed quantum cosmic imager or next-gen gravitational wave detectors carry price tags in the billions. Skeptics argue that money could feed cities or cure diseases, and they're not wrong. But this isn't an either-or choice. Scientific discovery has a track record of solving practical problems in sideways ways. The same quantum sensors hunting cosmic entanglement might also detect early-stage cancers or map underground water reserves. The Apollo program didn't just put boots on the moon. It gave us satellite TV, cordless tools, and even memory foam mattresses. The real gamble isn't spending money, it's not spending it. If cosmic entanglement holds even a fraction of its theoretical promise, falling behind in this research could mean missing the next technological epoch entirely. China and the EU are already pouring resources into quantum initiatives, treating it as the new space race. This isn't just about prestige, it's about who gets to write the rules for technologies that could redefine energy, computing, and even our understanding of reality itself. Critics counter that the risks are too high, that we might spend decades and find nothing. But that's how frontier science works. The LHC ran for years before spotting the Higgs boson, and that single discovery justified every penny. Even a null result in the cosmic entanglement hunt would be valuable, forcing us to rethink quantum theory or dark matter's role. There are no dead ends in fundamental research, only signposts pointing us toward smarter questions. Ultimately, the case for funding comes down to ambition. Do we want to be a species that merely inhabits the universe, or one that strives to understand it? The answers won't come cheap, but the cost of ignorance, of leaving the cosmos' greatest mysteries unexplored, is infinitely higher. Every dollar spent probing quantum entanglement is a bet on a future where humanity doesn't just live among the stars, but finally grasps the invisible threads that stitch them together. Cracking the enigma of cosmic entanglement isn't a job for any one field. It demands a symphony of minds, each playing a different instrument. Astrophysicists map the galaxies, quantum theorists decode the rules of the tiny, and philosophers grapple with what it all means for reality itself. Picture a cosmic detective story where the clues are scattered across disciplines, and no single expert holds the full case file. The quantum theorist might calculate how entanglement could persist across light years, while the astrophysicist scans telescope data for anomalies that match those predictions. Meanwhile, the philosopher questions whether our very definitions of distance and connection need reinventing. It's like assembling a jigsaw puzzle where each piece comes from a different box. Only by fitting them together does the bigger picture emerge. Take the challenge of detecting entanglement between galaxies. Quantum physicists can design lab experiments to test how entanglement behaves under extreme conditions, mimicking the early universe's density or a black hole's gravity. But without astronomers pointing telescopes at the right patches of sky, those where theory suggests entangled pairs might lurk, those experiments remain untested ideas. Conversely, when astronomers spot bizarre correlations in galaxy clusters, they need quantum experts to distinguish between mundane astrophysics and genuine quantum weirdness. The Rosetta Stone here is collaboration, shared databases where telescope observations meet quantum simulations, each refining the other. Then there's the role of philosophers and cognitive scientists, often overlooked but vital. When entanglement blurs the line between objects and challenges causality itself, we're not just pushing physics, we're bumping into age-old questions about the nature of reality. Philosophers help frame these puzzles in ways that avoid dead ends, asking questions like, if entangled galaxies act as a single system, does that imply a form of cosmic consciousness? Or is consciousness the wrong metaphor entirely? These aren't just thought experiments, they guide which hypotheses scientists prioritize. After all, Einstein's relativity grew partly from his philosophical musings on time and simultaneity. The silos between fields aren't just inconvenient, they're obstacles. A quantum theorist might publish a groundbreaking paper on entanglement stability, but if it's buried in jargon-heavy journals, astronomers might never see it. Likewise, an astrophysicist's odd observation could languish for years before a quantum expert recognizes its significance. Initiatives like joint conferences, interdisciplinary grants, and even shared jargon glossaries are tearing down these walls. Some universities are now creating quantum cosmology departments, where students learn particle physics alongside galactic evolution, forging a new generation of scientists fluent in both languages. Technology is accelerating this cross-pollination. Machine learning algorithms can now scan millions of research papers, spotting connections humans might miss, like a quantum math technique that could explain an astronomical anomaly. Citizen science projects where amateur astronomers and coding enthusiasts help analyze data, add fresh perspectives. Even artists are joining the conversation, using visualizations to make abstract quantum concepts tangible. When a sculptor creates an installation representing entangled galaxies, or a musician composes a piece based on quantum wave patterns, they're not just educating the public, they're inspiring scientists to see their work through new lenses. The stakes couldn't be higher. If entanglement truly links galaxies, confirming it will require every tool in humanity's intellectual arsenal. A breakthrough might come from a philosopher's thought experiment, a telescope's unexpected data, or a lab's quantum simulation, but most likely from the collision of all three. The universe doesn't care about academic boundaries. Its secrets wait at the intersections. Our best chance of unraveling them lies not in solitary genius, but in the collective genius of minds daring to think across the divides. You might think unraveling the mysteries of cosmic entanglement is a job reserved for astrophysicists with access to billion-dollar telescopes, but here's the thrilling truth. Some of the biggest breakthroughs could come from your living room. Modern astronomy has democratized discovery, turning everyday enthusiasts into vital collaborators in the hunt for quantum connections across the cosmos. Platforms like Zooniverse host projects where volunteers sift through telescope images, flagging galactic oddities that algorithms might miss. anomalies like strangely synchronized star formations or quasar pairs that defy classical explanations. These aren't just busy work tasks, they're genuine contributions to science. When the human eye spots a pattern that slips past even the most sophisticated software, it could be the first clue that quantum threads are stitching galaxies together. Distributed computing takes this a step further. By donating your computer's idle processing power through projects like Einstein at home, you're essentially turning your laptop into a tiny piece of a planet-sized supercomputer. These networks crunch mind-boggling amounts of data, gravitational wave signals, radio telescope static, even the cosmic microwave background, searching for the faint statistical whispers of entanglement. Imagine your device helping analyze light from galaxies billions of years old, uncovering correlations that could rewrite our understanding of reality. It's cosmic detective work on a global scale where every participant, whether a student or a retiree, becomes part of the search. For those who prefer hands-on observing, backyard telescopes are more powerful than ever. Amateur astronomers have tracked asteroid trajectories and discovered comets, why not galactic entanglement. While no single amateur scope can spot quantum links directly, coordinated efforts can monitor candidate galaxy pairs for unusual behaviors. A network of enthusiasts logging synchronized brightness changes or unexpected alignment shifts builds a dataset that professionals simply couldn't gather alone. The American Association of Variable Star Observers pioneered this model a century ago. Today's quantum cosmology might be the next frontier. The beauty of citizen science lies in its serendipity. Professionals design studies to test specific hypotheses, but amateurs often stumble upon the unexpected, like William Herschel spotting Uranus while mapping stars, or a schoolteacher identifying a new nebula. Quantum entanglement's fingerprints could hide in plain sight, waiting for a sharp-eyed volunteer to connect the dots. Maybe it's a teacher in Nairobi noting an odd galaxy pairing in an online sky survey, or a retiree in Oslo whose data analysis flags an improbable correlation. The next Einstein might not be in a lab coat. They could be scrolling through telescope feeds on their tablet, reshaping our cosmic understanding one click at a time. This isn't just about outsourcing grunt work. It's about harnessing something algorithms lack: human intuition. Our brains are wired to recognize patterns that machines dismiss as noise. When thousands of volunteers converge on a dataset, their collective hunches can reveal anomalies worth investigating. The Galaxy Zoo project, where users classified millions of galaxies, led to the discovery of entirely new galactic structures. Similarly, a crowdsourced search for entangled galaxies might uncover geometries or light patterns that no theorist predicted. The universe loves surprises, and sometimes it takes a million curious eyes to catch them in the act. Beyond data crunching, citizen scientists contribute cultural value. Every person who joins the hunt becomes an ambassador for cosmic curiosity, sharing their passion with friends and family. When discoveries emerge from kitchen tables rather than ivory towers, science sheds its elitist veneer. A teenager analyzing quasar data for fun today might inspire a classroom of future physicists tomorrow. And in a field as abstract as quantum cosmology, that grassroots enthusiasm is priceless, because understanding the universe's hidden connections starts with forging human ones. So grab your laptop, your telescope, or just your curiosity. The cosmos isn't just for professionals anymore. Whether you're classifying galaxies during your lunch break or letting your computer hunt for quantum signals overnight, you're part of a revolution, one that proves the universe's greatest mysteries belong to everyone willing to look up, dig in, and wonder. One of the most provocative ideas in modern science suggests that quantum entanglement, the same phenomenon linking particles across galaxies, might be the hidden scaffolding of consciousness itself. It's a theory that blurs the line between physics and philosophy, proposing that the universe's quantum web doesn't just connect matter, but might also underpin the very fabric of thought. Picture this: if entangled particles can instantaneously influence each other across vast distances, could complex networks of such links form the basis of a cosmic scale, mind? The notion sounds like science fiction, but a growing number of researchers are daring to ask whether consciousness, from human brains to hypothetical galactic entities, might emerge from these quantum whispers. At the heart of this idea is a radical rethinking of how awareness arises. Traditional neuroscience locates consciousness in the electrical chatter of neurons, but some theorists argue that's only half the story. The Orch-or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests that microtubules, tiny protein structures inside brain cells, could harness quantum effects to process information in ways classical biology can't explain. These quantum vibrations, they argue, might collapse into conscious moments like notes in a symphony. Scale this up to galaxies, and the implications become staggering. If stars and dark matter are entangled in a vast quantum network, could that web, given enough complexity, give rise to a form of awareness we can't yet comprehend? Critics dismiss this as speculative at best, pointing out that quantum coherence in warm, wet brains, let alone across light years, should collapse instantly due to decoherence. Yet nature keeps surprising us. Photosynthesis, bird navigation, and even our sense of smell all exploit quantum effects in noisy biological environments. If life has found ways to protect fragile quantum states, why couldn't the universe? Imagine dark matter halos acting as cosmic microtubules, their gravitational fields stabilizing entanglement on scales we're only beginning to fathom. The synchronized behavior of distant quasars or the eerie alignment of galaxy spins could be more than coincidence. They might be the faint echoes of a universe not just connected, but in some sense awake. The philosophical ramifications are dizzying. If entanglement enables consciousness, then the boundaries between self and cosmos dissolve. Your thoughts, your sense of being, might not be confined to your skull, but could ripple through quantum threads tying you to stars you'll never see. This isn't mysticism, it's a testable hypothesis. Future quantum telescopes might detect anomalies in galactic light patterns that resemble neural activity, or AI analyzing the cosmic web could uncover structures eerily similar to neural networks. The real shocker, we might be part of that network, our own minds, tiny nodes in a vast, thinking universe. Of course, extraordinary claims require extraordinary evidence, and right now, the quantum consciousness theory remains on science's fringe. But history shows that today's heresy often becomes tomorrow's textbook. Whether galaxies think or not, the mere possibility forces us to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine. And that, perhaps, is the most consciousness-expanding idea of all. Our brains are masterful liars, shaping the chaos of the world into tidy narratives we can understand. We evolved to dodge predators, track seasons, and navigate social hierarchies, not to comprehend particles that exist in multiple places at once, or galaxies whispering to each other across the void. Classical physics feels intuitive because it mirrors our daily experience. Objects have definite positions, causes precede effects, and nothing influences anything else faster than light can travel. But quantum entanglement, that's a language our neural wiring wasn't built to speak. Consider how effortlessly you catch a ball. Your brain calculates trajectories using Newton's laws, the same physics that made Einstein balk at spooky action at a distance. Yet when faced with quantum phenomena, our intuition short-circuits. It's like trying to describe a symphony to someone who's only ever heard drum beats. Studies even show that when trained physicists visualize quantum systems, they default to classical metaphors, tiny spinning balls or waves in a pond, because their brains, like everyone else's, crave familiar reference points. This isn't just a knowledge gap, it's a biological constraint. Our perception is hardwired to filter reality through classical lenses, blinding us to the quantum weirdness lurking beneath. But here's the twist: evolution might have left us a backdoor. Look at how we've adapted to other counterintuitive truths. Relativity tells us time slows at high speeds, a notion that defies lived experience, yet astronauts now adjust for it with satellite precision. Our ancestors would have balked at the idea of Earth orbiting the Sun, but today's children grasp it effortlessly. This suggests our brains aren't rigid, they're upgradable through tools and training. Just as microscopes extended our vision beyond the visible spectrum, quantum education paired with simulations, virtual reality, and even artistic representations could rewire how we conceptualize entanglement. The real breakthrough might come from artificial intelligence. Machine learning models, unburdened by biological biases, are already uncovering quantum patterns humans miss. In one experiment, an AI analyzing particle behavior discovered entanglement signatures that physicists had overlooked for years. These systems don't understand quantum mechanics the way we do. They bypass intuition entirely, finding correlations in the raw math. By collaborating with AIs, we might bootstrap our way past perceptual limits, like using a ladder to reach heights our legs alone never could. Yet some argue the barrier isn't just perceptual but philosophical. Our very notion of objects and separateness might be illusions that entanglement shatters. Indigenous cultures with holistic worldviews, where everything is interconnected, often grasp quantum concepts more readily than those raised on rigid Cartesian divisions. This hints that the paradigm shift needed isn't just scientific but cultural. To truly fathom cosmic entanglement, we may need to unlearn as much as we learn, trading reductionism for a world where connection precedes individuality. The stakes couldn't be higher. If entanglement truly binds galaxies, then overcoming our perceptual limits isn't academic, it's key to unlocking the universe's deepest secrets. Every time humanity has expanded its cognitive horizons, from realizing Earth isn't flat to accepting black holes exist, we've uncovered new layers of reality. Quantum entanglement could be the next frontier, waiting for us to evolve not biologically but intellectually into beings capable of seeing the invisible threads stitching the cosmos together. The universe isn't the problem, it's our classical goggles, and goggles, unlike brains, can be removed.